My name's Harper Baldwin, and I am a second-year master's student in the Arctic Coastal Geoscience Lab. My research focuses on Bering Sea storminess, assessing past impacts and future hazards utilizing traditional knowledge and flood mapping. So I'd like to start with the story of a storm. In September 2022, this storm, ex-Typhoon Merbok, moved into the Bering Sea. It formed off the east coast of Japan and moved northwestward toward the west coast of Alaska, particularly toward the Norton Sound region up in here. And in that region, it caused lots of damage due to flooding. So in Nome, flooding reached up to 5.4 meters above mean high or high water. And that's a term that I'll use throughout the presentation. It means the highest elevation that we expect water to reach during normal tidal variation. So water in Nome was 5.5 meters higher than the highest tide of the year. In addition, in Golovin, it was over 4 meters higher than mean high or high water. And this constituted a huge issue for infrastructure. As you can tell, lots of homes are inundated. This is a big problem. This storm was a 50-year storm, meaning that we only expect a storm of this magnitude to occur approximately once every 50 years. However, it was the second 50-year storm to occur on the west coast of Alaska in only 10 years. So this is satellite imagery of a storm that occurred almost 10 or over 10 years ago in November 2011. The satellite imagery looks really similar, as you can tell, and it caused similar damage in the Norton Sound region. So is this frequency and severity of storms on the west coast of Alaska an anomaly? Unfortunately, we don't think so. The frequency and severity of storms could increase with predicted climate changes in the Bering Sea. In addition, environmental changes such as increased temperature and decreased sea ice and permafrost could increase the severity of storms once they hit communities. In addition, these storms affect marginalized Indigenous communities where data on past impacts is limited, which is a huge issue because we used the impacts of past storms in order to predict future impacts. Therefore, research to characterize these historical storm impacts and identify at-risk infrastructure and livelihoods is necessary. But before I get into more of my research, I'd like to go back to this storm and talk about my experience during it, because I had the good timing to be located at one of my thesis sites, St. Paul Island, when the storm came through. So I was right in the central Bering Sea when this storm came through. And it was a pretty wild experience. Here's a video during the storm. And you can't hear the sound, which is totally fine because all you can hear is wind, basically. So that video took place before peak storm surge. So it actually got worse than that. And we were inside when it hit peak for that reason. So we couldn't survey that day, of course, because our bodies nor our equipment could really function in the 60 to 80 mile per hour winds that were hitting the island. But we were able to kind of drive around and see all the flooding as it occurred, which was really great for my study because I'm, wondering what will happen when big storms hit this community. And I got to really see in real time what happens when a huge storm hits St. Paul Island. Luckily, no one was injured and no major infrastructure was damaged. But as you can see, it inundated roadways and generally caused a lot of trouble on the day of the storm. As soon as the storm was over, we got to work trying to take as much data as we could about the storm and really understand exactly what had happened on the island. And one of the big tools that we use to characterize storm impacts is drones. So this is drone footage of a marine debris cleanup after the storm. And this is a really great way to kind of qualitatively assess exactly how much damage occurred during the storm. You can see a lot of trash, which is a huge environmental problem in St. Paul. Tons of marine trash wash up on shore every year, and the local community members need to go out and clean it up because there's no one else to come do that. So you can see all the trash here, and you can see how clear the high water mark from the storm was. So it's very clear in this drone imagery exactly how high the water got, which we were able to use to delineate the storm height with our survey drone. So we took our survey drone out and we were able to fly and create this composite image that shows exactly how high the water got at Antone Lake, which is an important recreation site on the island. And this was actually one of my favorite places to witness during the storm. You can see before the storm, there was a road and a rocky beach to the right of the road that locals indicated had never been overtopped with water in their lifetime. But during the storm, it was clearly being overtopped with water. So this seems like, the biggest storm that has occurred in people's lifetime on St. Paul. There was so much energy from the wave action that boulders were rolling onto the road, and as was, hundreds of pounds of driftwood, which you can kind of see down here in the post-storm imagery. So that road is totally covered with debris now. The most important data set that we collected during our time out there was the high watermark data set. So we have an incredibly accurate GPS system that takes the X, Y, and Z coordinates of a point in space with 3-centimeter accuracy. So we were able to really pinpoint exactly how high the water got throughout the study site. And this fed into a larger response initiated by a number of institutions listed down here at the bottom. So a bunch of people who didn't have the good timing to be at their field site already during the storm flew out to all of these places listed in blue in here to assess high water marks on the west coast of Alaska. And locations where the same protocol was done in 2011 are listed in red. So you can see how much bigger the response was to this storm than the storm in 2011. In addition, you can see in black the number of NOAA permanent water level gauges that are deployed on the west coast. So in a lot of regions, like down in here, our high water marks are some of the only measurements that we really have of how high the water got. So these high water marks are really important for coastal planning because, again, understanding future storm impacts is greatly aided by understanding historical storm impacts. However, we hope that another storm like this doesn't roll through for another 10 years at least. So how can we expand the temporal resolution of our data set? Well, luckily, people have lived on and stewarded these coastal lands for thousands of years. So by partnering with local experts and incorporating traditional knowledge into our data set, we can add more points. So this is one of the major goals of my thesis, is to conduct interviews in St. Paul Island and Good News Bay to improve this data set. This is me trying to get people to come talk to me about storms. I set up a local store in Good News Bay and handed out maps to people who wanted to talk about storms and impacts. And then using interview data, we were able to measure with our very accurate GPS system exactly the height that flooding reached at past storm events. So this is from 2011, or this is a point that we took in 2022, but that references a 2011 storm. And while we're in communities, we also take the height of important infrastructure like the cemetery or first floor heights of homes that are in a flood zone, so that we can really accurately figure out when different infrastructure would potentially be inundated and by what flooding events. So we put all of this data together into these flood hazard maps. And I made this map for St. Paul. It depicts historical flood heights as well as potential future flood heights based on increased storminess and sea level rise. And it also highlights infrastructure that has the potential to be inundated by storm events. So these help communities potentially plan the movement of major infrastructure. And with this work, we aim to increase the spatial and temporal resolution of our historical high water mark dataset to improve coastal resilience, address local research priorities, and help communities prepare for climate changes. Thank you.